Good. So, hello everyone. Today we are first gonna talk a little bit more about SQL, and probably we will still have enough time to start with a new topic, which is about looking at how your data is actually stored on the computer. Now, last time we have seen one very important feature of SQL, which is that you can essentially nest SQL queries, so-called subqueries, within a larger surrounding query. So you can use a SQL query as part of a SQL query, basically. And the last time we have seen a couple of very simple examples for that. Here you see one of them. Here we are selecting the student names from the students table where the GPA is greater or equal to the maximum GPA across all students. And in order to calculate this maximum GPA, we are actually using a subquery. So here we have one query marked up in red here, which selects the maximum GPA from the students table. And then the result of that query is used as an operand within the where condition of the surrounding query. So that is one possible use case for subqueries. We can also use them in other parts of a query. All right. Now, in the last example, we have seen one possibility to include a subquery into a larger query. There's many more ways in which you can do that. Here you see a couple of more ways in order to integrate subqueries into the where condition or into conditions in general of your query. And one operation that you commonly use in the context of subqueries, that is this exists expression here, and that essentially checks whether the result of a subquery is empty. And we'll also see some more examples on that. So that is commonly used. Or for instance, you could check whether one specific value is within the result values produced by a subquery, and you can do this using the in keyword that we have already seen, but so far we have seen it for checking whether one value is within a list of constant values, and here we are using it to check whether one value is within the results returned by a subquery. Another thing that you can use is the all and any keywords. And here essentially you use that in order to test whether some condition is satisfied either for all result rows of a subquery or for any, meaning for at least some of them. And in that case, the corresponding condition returns true. Let's perhaps see one more example for the last possibility here. What we are doing here is we are selecting the student name from the students where GPA is greater or equal all result rows from this subquery that selects GPAs from students. And can anyone tell me in the chat what you believe that this query is doing? Anyone, any ideas? Yeah, exactly. So here I have multiple propositions. Yeah, so multiple times the same propositions actually. So that is correct. So here we are again essentially checking for those students where the GPA is greater or equal the GPA of all students. So in the end, that comes down to searching for the students with the maximum GPA. Yeah. All right. And one last question is whether the result of this, I assume it means the result of the where expression, whether that can be false or null. So here, I mean, it could be it could be null if we have, for instance, some null values for the GPA. If there's some students where I don't know the GPA, I cannot verify whether one specific student has the highest GPA because I don't know the GPA of some of the other students, right? And I mean, for this to be false, that is the case if there is another student who has a higher GPA than the currently examined student. So you can imagine that here we are iterating over the students that are stored in a student table. We are picking one, then we check whether this condition that student's GPA is greater or equal the list of all GPAs from all students for each of them. And if that is the case, I'm going to include it into the result. If that is not the case, I'm not going to include it into the query result. Right? So we can essentially imagine that we have a for loop pretty much where we iterate over the students, and then the subquery would essentially correspond to another for loop. So we have like essentially two nested for loops. Both of them are iterating over the students. Yeah? Okay. All right. Now, those are a couple of examples for subqueries. Essentially, you just evaluate the subqueries first for the examples that we have seen, and then you get some kind of return value. Then you insert that return value into the surrounding query. Now, what we have seen so far is what we call uncorrelated subqueries. And that means essentially that you could run the subquery all by itself and the database management system would not complain. Correlated subqueries are a little bit more difficult. This is why we are doing them now, and we started with the other ones. For correlated subqueries, the nested query, the subquery, is not independent from the surrounding query. So here the subquery would essentially reference some elements that appear in the surrounding query, which means that a subquery all by itself is not viable because it would include references to something that only exists in the outer query, right? And so here, by the way, I see some interesting discussion going on, and I encourage you to generally answer the questions of your classmates also in the chat. And just because I see that here, let me say one last thing about the evaluation of this subquery that I have shown here. I told you that you can imagine that this is evaluated by two nested for loops. And here, one of the questions is, wouldn't that be inefficient? And I actually agree with that. So if I say that you could evaluate it with two nested for loops, I just mean conceptually, this is how you can imagine what the query result is going to be. You can essentially, in order to understand what the result of this query is, you can imagine that we would have two nested for loops. But internally, the database management system is probably doing something more efficient, or could be doing something more efficient. And the way in which you write your query generally is independent of how the database management system evaluates your query. So the two for loops, this is not necessarily what's happening inside, but this is what you can imagine is happening in order to understand what the result of this query is. Okay, very good points here in the chat. All right, and now we are switching to correlated subqueries which reference something outside of the subquery and in the surrounding query. Now, let's see a first example. Quickly need to move the chat so I can see the example fully. All right. So here we are again selecting the student names from the students table, and we assign the alias S1 to it in the outer query. And the condition to be included in the result is that the s1.gpa must be greater or equal to all. And here comes a select over students again. This time we assign a different alias s2. And we require that s1.sname equals s2.sname. So can anyone first of all tell me why this is a correlated subquery? Looks kind of similar to the ones that we have seen already. So what makes this one specific? Yes, very good. And here there's the reference to, in particular, S2. So within the, in particular, S1. So here within the subquery, we are referencing table alias S2 and table alias S1. Now, table alias S2 is not particularly exciting because that is defined within the same subquery. Table alias S1, on the other hand, that one is actually not defined within the subquery, but it is defined outside. It is defined in the outer query. That means if you take the subquery, select s2.gpa from students s2, where s1.sname equals s2.sname, that subquery marked in red, and you run it all by itself in a database management system, you will actually not be able to do that because the database system will complain to you that there is some undefined identifier S1. And that's why it is a correlated subquery. So yes, so this is why it is a correlated subquery. And can anyone guess as to what this query is actually doing? So strictly speaking, we have not yet discussed in detail how to evaluate those correlated subqueries, but maybe anyone has a hunch about what this could be. Very good. And here I see the right solution popping up. So what it does is actually the following. So I'm again gonna tell you how you can imagine that this query is evaluated, even though internally inside the database system, it might be evaluated in a more efficient manner. But what you can imagine here is that we are iterating in the outer query, we're iterating over the students again. And for each of those students that we are iterating over in the outer loop, so to speak, we are iterating over the students in an inner loop. And within that inner loop, we are only considering students which have the same name as the currently selected student in the outer loop. And then we check whether for all of those students which have the same name as the students in the outer loop, the GPA from the outer loop student is greater or equal to the GPA of the inner loop student. S1 and S2, basically, those are like two iterator variables. Okay, and because of that, as suggested here by one of your peers, we do indeed retain those students, the name of students, which have the maximum GPA among all the students with the same name. So that's maybe a little bit of an artificial example, but of course, in principle, you can have students with the same name, even though not the same net ID. And here we are keeping the maximum GPA student among all groups of students with the same name. One thing that I used here, by the way, besides introducing correlated subqueries, I have one query where the same table appears multiple times. We have already seen that before, but just to point your attention towards that. So in general, you can have the same table appear multiple times in a query, either within different subqueries or even like within the same query. But what you often want to do is to assign different aliases to that same table. So here I have the students table, once appearing with S1 and once appearing with S2. And one interesting question that I see here So whether this query would be possible without two aliases to students. And here, I mean, if you want to, I mean, you could probably reformulate the query in quite a different way. And maybe you could get around that. But I mean, definitely as long as you stay with this structure of the query, here you need to compare students of the same name. So you need to compare two students. And in order to distinguish between those two students, you need to use an alias here. Yes, exactly. So that's why I'm saying that if you keep the same structure, then you need to do this. It would also be ways, for instance, to group by the names, get the maximum GPA in each group. That is a great suggestion. And then joining that with the, and then joining that in order to get the student associated with the maximum GPA within each of those student groups. Or you could, for instance, use a subquery in the from clause, and then you would have to introduce an alias for that subquery, but strictly speaking, not for the table alone. Okay, so there's many ways of writing this, but you need some way of correlating different students in order to make this comparison. All right. So the general principle, in order to imagine how the result of those correlated subqueries is generated, I find it quite convenient to imagine nested loops being evaluated, even though that might be inefficient and not what the database management system is doing in the background, but it can help to imagine that. And then you would generally iterate over the rows in some outer containing query. And for a fixed row, you would evaluate the inner query. Now here, the result of the inner query might depend on which row is currently selected in the outer query. That is why, at least conceptually, we would have to re-evaluate the correlated subquery for each different row in the outer query. And then if the where condition in the outer query uses a subquery, then finally you would decide for the currently selected row in the outer query whether to include it into the result set or not. Now, here, for instance, we have another example. So here again, we are comparing students, and we use a correlated subquery. So here we, in the outer loop, iterate over the students again. And then for each fixed student in the outer loop, we check whether the result of this correlated subquery is non-empty. That is what the exists keyword is doing. There exists some result. And for a fixed student in the outer loop, in the inner query, I'm iterating over the students again. And I check whether there is another student who has a higher GPA. Now, and if such a student exists, then the outer loop student will be included into the result set. So what this is basically doing is that here, this time, we're selecting the names of all the students except for the students with the highest GPA, because for each student we test whether there's another student with a higher GPA, right? So those are a couple of simple correlated subqueries that you see here. Now, take a look at this one. Now, what I'm exploiting here is the fact that actually your subqueries can also have subqueries. So you can have multiple levels of nesting. And here, in this query, we are first iterating over courses. Then next, we are iterating over students. Then next, we are iterating over enrollments. Does anyone have an idea what this query is doing? Any propositions? Okay, first proposition, find courses that have no students enrolled in them. Find the courses that have no enrollment. Okay, other propositions? In order to break that down, so that is perhaps the most complex query we have seen so far. Okay, so let's break it down a bit. So let's make it simpler by imagining that we have already fixed one course in the outermost loop. Now, can anyone tell me what the result of this select star from students and so on, what the result of this query is gonna be? So we have fixed the course, and now we have this query select star from students S, where not exists select star from enrollment E, where course ID matches and student ID matches. Find courses with at least one student enrolled. Okay, that is all right. This is the right direction here. Okay, I'm gonna give it a second because I think it's a nice example and makes sense to think about it for a few seconds. Okay, good propositions here. Okay, I'm gonna resolve it in a minute. Just okay, people are agreeing. Is that agreeing to the solution, perhaps? Okay. All right, so I give it one more minute and just think about it a little bit more. And clearly, as the exists keyword tests whether the result of a subquery is non-empty. Not exists essentially tests whether the result of a subquery is empty. And it is true only in that case. All right, so let's have a look at this. So let's maybe start with the innermost subquery. So what we're doing here is that we're looking at the enrollment information, which links students to the courses that they are enrolled in. Okay, and the student as well as the course, they have been fixed in the outer queries currently. So here I'm essentially checking whether some enrollment information exists for the currently selected course and for the currently selected student. Now, this innermost subquery is contained within a not exists clause in that middle query, which selects from the students table, right? And so basically here in that middle query, I am producing students which are not enrolled in a specific course because the enrollment information for this student with the currently selected course in the outer query is empty. Okay, so here let me maybe mark that here. So here this query essentially looks for students that are not enrolled in the currently selected course. And now I'm looking for courses where the result of this subquery is empty. So I'm essentially looking for courses where no student is not enrolled. So that formulated differently means that here I'm looking for the students, for the courses where all the students are enrolled, which most likely is empty, the result of that query. But that is what the query is looking for. Here I'm fixing a course. Then I'm looking for students which are not enrolled in that course. And then I'm checking whether that list is empty, so no student is not enrolled in the course. And if so, I'm including the name of this course into the result set. That's what this query is doing. All right. So that is what we will see about SQL. Now, this is probably the most difficult query that we have seen in the course, and I encourage you to think a little bit more about it and to make sure that you understand what's going on there, and also perhaps to experiment a little bit with some with some nested queries yourself. For instance, in the data set that we have recently downloaded, or in some other data set of your choosing. We have seen a couple of examples, but in the end, to really get the hang of it, you probably want to write some queries like this yourself. And I encourage you to do that. All right. So maybe looking for some questions. Mm-hmm. Okay. All right. So that was everything that we will see about SQL. This will also be the topic of the first homework, by the way, which we will release on Monday next week. So I encourage you to have another look at the examples that we have seen in class, and perhaps also try out writing SQL queries for yourself a little bit. And you can either do this with your local Postgres installation, or I've also shown you the website DB Fiddle, which allows you to write and try out SQL queries without any local installation. Okay. Now, next, I want to turn to a bit of a different topic. So now we have seen essentially what is the interface of database management systems. And now we will see in the following a little bit more of what is going on inside of the database management system. So first of all, we're going to talk more about how the data of your database management system is organized and stored. So here we are at the lower part of this diagram that I have introduced in the first lecture. The relevant chapters in the Ramakrishnan and Gerke book, those are chapters 7 and 8 in particular. And what we are going to do in the following is that we are first going to discuss about the hardware on which data is stored. And then we're going to discuss a little bit about the format according to which data is stored on that hardware. So in the following, we're going to first discuss about the hardware on which your data is stored. And the properties of that hardware will motivate certain design decisions in the database management system. Now, data on your computer is generally stored on different locations, and typically those possible locations are represented as this memory hierarchy that you see here. It's often represented in this pyramid shape in order to illustrate that the capacity of the storage layers decreases once you go up that pyramid. So typically the storage layers towards the upper part of this pyramid, they have faster access times, but they also have fewer, less capacity, so you can store less data there. Another important distinction between the different layers of the memory hierarchy is that some of them are volatile, meaning that data there is erased once your computer switches off, while others are permanent, meaning that even if your server switches off, then they will still keep the data stored. And at least traditionally, database management systems, they consider, for instance, updates to your data only as secure once those updates reach stable storage. At the very top of that pyramid, so to speak, sits the CPU, which is doing the actual processing. So what needs to happen in order to do any useful computation over the data is that you move the data through the memory hierarchy up to the processor registers where the processor can access it. Now, in the following, we're going to go through those different layers of the memory hierarchy and get a sense a little bit for what those storage devices look like and what kind of properties they are featuring. All right, so at the very bottom of that memory hierarchy, we have typically those tape storage devices. And you see one of them in the right upper corner. Now, those tape storage devices, they work according to the same principle basically as those music tapes that are not very common anymore, but probably you have seen one already. Those tapes generally store information. They store bits as a magnetic information on that tape. Now, once you have positioned your tape at the correct position, where the data you're interested where you are interested in is located at. In that case, you can get quite reasonable speeds for reading and writing data. It's not going to be fast, but it's not going to be terrible either. The problem is that it might take quite some time until you bring your tape into the position where the data you're interested in is located at. So that might take seconds, tens of seconds even, which in the context of data processing is completely awful, of course. But on the pro side, those tapes are extremely cheap. So I have put a couple of numbers here, and please take those numbers with a grain of salt, because they keep changing over time, and it also depends on which specific devices you are considering. But I think that those numbers, they give you some intuition for how the different layers of the memory hierarchy relate to each other. For that, the numbers are useful, but don't take them too serious either. So the nice thing about tape storage is that it is very cheap. You can store a lot of data for without paying too much money. And that's why it is quite popular for long-term archival storage. So also cloud providers like Google, for instance, they would use tape in order to store backups. So we are not going to discuss that much about a tape storage because the database management system typically assumes that you can access data faster than this. But if you're interested in reading up more, then here I have a link to a corresponding article in the slides. Now the next higher level of the memory hierarchy, that is hard disk. And hard disk, that is a popular storage medium. And a large part of traditional database management systems, they have been designed under the assumption that the bulk of your data is actually stored on hard disk. Hard disk represents bits in a similar manner as the previous storage medium as magnetic information again, but this time we are writing this magnetic information on a round disk, such as the one that you see on the right upper side. So you see here there is indeed a round disk or even multiple stacked disks in the middle of that hard disk. And in order to access data you're interested in, you have to do two things. So first of all, this disk containing the magnetic information, it is spinning with a very high frequency, thousands of spins per minute. And you are reading and writing data on that disk with so-called heads, for which you can choose the distance between the middle of that disk and the head. So you can move that head into one direction in order to access different parts of the disk. And as the disk is already spinning, once you have positioned your head properly, you just have to wait, essentially, until the data you're interested in comes rushing by as the disk turns, right? So once we have positioned those heads properly, then again, we can read data at reasonable speeds and write it at reasonable speeds. Again, one problem is that it can take a little bit of time to position that read-write head properly. It can take some tens of milliseconds, which is of course much faster than before, but still in the context of data processing, it is kind of long. So hard disk is not considered a very efficient high performance. At least in terms of speed, let's say, it's not considered the medium of choice. On the pro side, again, it is more expensive than tape, but it is still quite cheap. So that's why you might want to use it for less frequently accessed data. And indeed, traditional database management systems, they assume that you typically store the data that is not immediately used on hard disk. A little bit over the hard disks are those solid state drives, which use a different technology to store bits using a small electric charges. They have a comparatively elevated price. Here, those numbers are already slightly outdated, but you see they are significantly higher than for a hard disk. You have in exchange a pretty fast access because you don't have any moving parts, you don't have any mechanical parts that you need to reposition, like the diskettes, for instance. And you can also at least read speeds at quite at elevated rates, let's say. One problem with those devices is that the number of write cycles that you can do is limited. They wear out, but people have been looking into techniques in order to at least partially overcome that, in order to, for instance, have some spare capacity in order to replace cells that fail because you have too many writes on them, and to try to partition the writing load equally on those devices. So we're not gonna discuss that into much detail, but just to give you some little overview of the pros and cons of that storage technology. Main memory, that is the next level of the memory hierarchy. And here we have a big jump in terms of access speed. Again, we are storing bits as small electric charges. And compared to the other storage media, main memory is quite expensive for storage, if you look at the price per gigabyte, for instance. But on the other side, you have some very fast access times. You can read and write data at a relatively high bandwidth. So this is a very significant difference to the storage media that we have seen before. So traditionally, main memory is used in order to hold data that you're immediately working with. And if you can afford it nowadays, more and more people are even able to fit entire databases into main memory. If you have hundreds of gigabytes or terabytes of main memory, that might be feasible. Of course, you have to pay a little bit for it. So there's a big jump in terms of access efficiency between hard disk in particular, also SSDs, and main memory. So in traditional database management system design, we are actually assuming that, the main overhead when it comes to data movements is for moving data from hard disk into main memory. And as we will see in much more detail later, therefore, we try to be efficient about when and what data we move from hard disk into main memory. So main memory and a hard disk, those are typically considered, one for storing the bulk of your data, one for storing the data that is immediately relevant, even if nowadays, more and more often you can fit significant parts of your database into main memory. Finally, we have the CPU caches, and they are typically organized as a hierarchy. So you have not only one cache, but you have L1, L2, and L3 caches. And from L1 to L3, typically, we increase the capacity, but access time increases as well. Now, clearly, those caches are very expensive per gigabyte, so we cannot make them all too large. But on the pro side, they offer essentially near instantaneous access and very high bandwidth. So that data is typically currently being used for some operation, or it has at least been used recently, or it is close to data that has been used recently. So you cannot fit that much data into those caches, but if you can fit data into it, then you have extremely high access times, and that makes it very efficient. Now, the final layer of the memory hierarchy, that would be the registers, but I mean, the registers, they are basically what the processor can access immediately. So I'm not gonna discuss this in detail. So now we have seen a little overview of the different storage layers in your database management system. But we want to discuss about database management systems. It's not a hardware call, right? So I mean, how does the properties of those storage layers relate to design decisions that we make in a database management system? And it will turn out that for the next couple of weeks, many of the things that we will be discussing, they only make sense due to the property of those storage media for data. And so I want you to internalize those high-level points that I'm noting down here, which illustrate a little bit how those storage media properties influence the design of database management systems. So I mean, generally what we have seen is that the capacity of those upper layers of your memory hierarchy is limited. And that means, since we are generally dealing with large data sets, we have to assume that at least one part of our data set is stored on one of the lower parts of that hierarchy, where we have some significant access times. And that is important because typically, if you have been looking at algorithms like sorting algorithms, for instance, you have been looking at the number of computational steps that they are performing. You have compared different algorithms by how many computational steps we are performing. But in the case of databases, if you're dealing with very large data sets, then because you often cannot fit them into the efficient layers of the memory hierarchy, you have to account for overheads just for accessing data, not even doing the computation. If you have, for instance, your data located mostly on hard disk, then just the time for accessing that data, for moving data through the memory hierarchy, that often dominates your total execution time. And this is why many of the algorithms that we will see in the following that are used by database management systems, they are not optimized for minimizing the number of comparisons, for instance, but instead they are really optimized for minimizing how often I need to load data, for instance, from hard disk, right? So we want to design our algorithms in order to minimize data movements. Another property of those devices, we have often separated the bandwidth for reading and writing data and the time for accessing data that was located, for instance, somewhere on the disk. And then in order to access some random location in your data, you have to do things like rewinding the tape or like repositioning your diskette, and those things, they cause quite some overheads. So random data access is often very expensive with those storage media. So that's why once you have already repositioned your diskette, you don't want to read one single bit, but you want to read a reasonable chunk of data to make it worth your while, to pay for all that overhead. That is why we will see in the following that we are generally accessing data in chunks of data, which we will also call pages in the following. And the reason is that doing that is often more efficient than accessing a very small units of data. Another thing that we will see later is that because we can quite cheaply read data that is close together. For a hard disk, it doesn't require you to reposition your diskette, for instance, right? So you can read close by data quite efficiently. And that motivates us to design data structures that keep related data close together in order to make the access more efficient. That's also something that we will see in the following. And one topic that we will discuss about much more in later lectures of this course is the topic of volatility. Because once your database processes updates, as long as those updates are only written in main memory, they could get lost if your server suddenly loses power, for instance. And database management systems, they use quite sophisticated strategies to make sure that your updates are secure, and that even if you suddenly lose power or some other catastrophe happens, that your database remains in a consistent state. And those strategies need to be very aware about which level of the memory hierarchy your data currently resides on, and whether that level is volatile, meaning it loses data once the power switches off, or not. So I want to end with those high-level points. Please internalize them, because without them, many of the things that we will do in the following lectures, they won't make that much sense. So I often get questions about why we do things in a certain way, which could be answered by those high-level points here. The next time, we're going to look more into data storage formats, and we're going to start with indexing. Over the weekend, I encourage you to revise the material that we have seen about SQL queries, because on Monday next week, the homework which focuses on SQL queries will come out. All right. Have a nice day, and I wish you a nice weekend, and then we see you again on Monday.